In 2018, one GitHub CI script made 40,000 API calls in a single minute. No bouncer at the door, no counter, nothing checking who came in. Every production API needs a bouncer, someone counting heads and deciding who gets in right now. That bouncer is called rate limiting, and today you'll learn exactly how he thinks. Cloudflare blocks 60 billion malicious requests every single day. Twitter's 2009 API got scraped by bots at 100 times its intended rate before anyone stepped in. GitHub caps you at 5,000 requests an hour. Cross it and you're locked out instantly. This isn't paranoia, it's survival. Imagine a club with zero bouncer. One person buys 500 drinks and resells them outside. Real customers can't even reach the bar. Your API without rate limiting works exactly like this. One bot or one buggy script monopolizes every server thread while paying users get nothing but timeouts. Here's the flow with zero protection. Request arrives, server processes it, no matter how many show up. At 10 requests a second, fine. At 10,000 a second from one script, your database connection pool dies, and it drags every single user down with it, not just the offender. The first fix engineers reach for, the fixed window counter. Pick a 1-minute window, count requests, reset to 0 at the top of each minute. Store it in Redis with a TTL equal to the window. Dead simple, memory cheap, but simple comes with a hidden cost you'll see next. Here's the flaw. A client fires 100 requests at 12:59, window 1, then fires 100 more at 12:01, window 2. Two separate counters, two separate limits. Result, 200 requests in 2 seconds. The bouncer resets his head count exactly at midnight and everyone rushes the door at once. Here's what nobody tells you. Adding more API servers actually breaks your rate limit. 10 servers, 10 separate counters. A client hitting all 10 gets 10 times the allowed rate, completely undetected. This is exactly how GitHub's 2018 CI outage happened. One script blew past every local counter and slammed the database with 40,000 calls in a minute. The accurate fix. Sliding window log. Store every request timestamp in a sorted set. Drop old ones, count what's left. Zero boundary bugs. But at 1,000 requests an hour across 10,000 users, that's 10 million timestamps sitting in memory. Accuracy, it turns out, is expensive. Cloudflare's answer, blend the current and previous window. Weight the previous count by how much still overlaps. Window is 60 seconds, 45 have passed. Previous had 80 requests, current has 30. Estimate 80 times 15 over 60 plus 30 equals 50. 2 Redis reads, constant memory, good enough. Remember the bouncer? Token Bucket is his wristband system. He hands out N wristbands up front, refilling at a steady rate, say 10 a second. Got a wristband, you're in. Bucket's empty, you wait. This lets a burst of eager customers through, then throttles to a sustainable rate. Here's how Stripe actually runs this. Client sends a request with its API key. Server calls a Redis Lua script, Atomic, so 2 requests can't race each other. It checks tokens, refills based on elapsed time, deducts 1, returns allow or reject, all in about half a millisecond. This is the exact pattern production systems use. Read tokens and last refill time. Calculate new tokens, elapsed seconds times refill rate, capped at capacity. If at least 1 token remains, deduct it and allow, otherwise reject. All inside one Atomic Lua script, no race conditions possible. Leaky Bucket is Token Bucket's stricter cousin. Requests queue up, then drain at a perfectly constant rate, like water leaking from a hole. No bursts ever. Great for smoothing network traffic. Bad for APIs, because legitimate bursts now sit in line, adding latency users can actually feel. So how do you stop that 10-server exploit from earlier? Centralize the count. Every API server checks the same Redis instance before allowing a request. One shared bouncer, not 10 confused ones. It costs about 1 millisecond of latency, a small price for actually enforcing the limit. GitHub's real numbers. Unauthenticated requests get 60 an hour. Authenticate and you jump to 5,000. GitHub Actions gets 1,000. They use fixed window counters reset at the top of every UTC hour, plus secondary limits like 80 content creating requests a minute to catch abuse hiding under the cap. Stripe runs pure Token Bucket. Default, 100 requests burst capacity, refilling at 100 per second, sustained. Every response carries X rate limit headers showing exactly how many tokens remain. Their Lua script adds half a millisecond of overhead, invisible to your app, invaluable to their infrastructure. Cloudflare processes 60 billion of these checks daily across 1,000+ edge locations. They chose the sliding window counter, accurate enough, constant memory, only 2 Redis operations per check. Regional Redis clusters aggregate counts so attackers can't just spread requests across data centers to dodge the limit. Every well-designed rate limiter talks back. It returns X rate limit, X rate limit remaining, and X rate limit reset on every response. Hit the ceiling and you get a 429 with a retry after header. Well-behaved clients read that and back off. Badly behaved ones just get blocked harder. The part every tutorial skips. Doing this without Atomicity. Read the count, check it, then increment 3 separate steps. 2 requests can read the same count at once, both pass the check, both increment. Congratulations, you just let 2 requests through when your limit was 1. The fix: wrap read check write in one atomic Lua script. Redis executes it as a single, uninterruptible command. No other request can sneak in between the check and the increment. This one decision is why Redis Lua scripts became the industry standard for every algorithm we've covered. Rate limiting isn't just defense, it's a sensor. Track how often each client hits the ceiling. A sudden spike in 429s from one IP is often the first sign of a bot, scraper, or compromised API key, long before it becomes a headline outage. So which algorithm wins? Fixed window, fast but bursts at boundaries. Sliding log, perfectly accurate but memory hungry. Sliding counter, Cloudflare's pick, fast and close enough. Token bucket, Stripe's pick, handles bursts gracefully. There's no single right answer, only the right trade-off for your traffic. In your next system design interview, say exactly this. I'd use Token Bucket for burst-tolerant APIs like payments, sliding window counter for high-volume edge traffic, and always enforce it atomically with Redis Lua scripts to avoid race conditions. That sentence signals you've actually built this before. Zoom out and you'll see this everywhere. AWS API Gateway defaults to 10,000 requests per second. Twitter's free API tier now allows just 1,500 tweets a month. Every major platform you've ever used is running some version of this bouncer at its front door right now. Here's the evolution in one line. Fixed window came first for simplicity, sliding log came next for accuracy, sliding counter balanced the two, and token bucket became the production favorite for real-world bursts. Each algorithm exists because the last one had a scar from production. Back to our bouncer. Cloudflare's version rejects 60 billion people a day, across 1,000 doors, without ever losing count. Stripe's version hands out wristbands in half a millisecond. That's not luck, that's a handful of these algorithms running quietly on every request you'll ever make. The bouncer never sleeps. He just counts wristbands, resets his clock, and refills the bucket forever. Next interview, tell them about the bouncer. Subscribe for the next breakdown. How consistent hashing keeps that bouncer's replacements in sync across 1,000 doors.